Good morning, everyone, and welcome back to Math 115. So today we are going to talk about the next section. Actually, we're still talking about section 2.4b. Oh, no, we're not. We finished 2.4, didn't we? What am I doing? We finished 2.4, and now we're going to talk about 2.5. Okay, so homework 2.3 and 2.4a are due Thursday. That's today. And 2.4b is due tomorrow. But there's only like 3 questions. There's very few questions on 2.4b because we didn't talk about oblique asymptotes. So that's the homework. Your next assessment is going to be the exam, and that will be on the Wednesday after fall break. I have office hours today from 2:30 to 4 p.m. in my office. Can I have a show of hands on who's planning on coming? Okay, not too many people, so I'm going to have them in my office. Unless a lot of people show up, then we will move to a classroom. By the way, with the new kind of format of the class, which we are trying out, okay, the format is going to be, let me just remind everyone, I'm going to try to give basically a very short informational dump, okay? And then I will let you all loose on some problems, okay? And the goal of this is to allow you to learn the mathematics better by doing it than by listening to me and watching me do it, right? So with that in mind, the problems that I'm going to assign for the class activities are going to be somewhat harder than you might expect to see on an exam or a quiz or even on the homework, okay? And the reason that I assign the slightly harder problems is because, first of all, you get to work in groups, right? Which means you get to put your heads together and do something a little bit more challenging that allows you to see like what are like the fundamental principles that are underlying these problems. And second of all, what was the second of all? I don't know what the second of all was, but basically it's just that one thing, I guess. So what I mean to say is that these are challenging problems, and it's possible that you and your partner maybe don't finish solving those problems, okay? But the way that we're doing the class, it's not necessarily going to allow me to have a lot of time to go through these examples in detail. I'll give some of the more kind of important notes on these problems. But if you want to see them solved in detail, you must come to office hours or go to the Math Tutoring Center, okay? So that's a little bit of the expense that we pay by having the group work, but I think that the group work is really helpful for you all. Okay, so that's what I want to say about that. So any administrative questions before we start in on content for today? Yeah. Yeah. This is strange. It's usually already off. Better? No problem. Any other questions? Okay, then let's start. So I will remind you briefly what we talked about last time, which was basically the behavior of a rational function near a vertical asymptote. And that was really the last thing that we had to kind of finish up before we were ready to start in on doing everything all together to graph a rational function. Okay, so everything all together, it went like this. We need to find the x-intercepts and the y-intercepts, okay? For the x-intercepts, we need to also determine the nearby behavior, okay? So does it pass through? Does it bounce off? What's happening, right? Based on the multiplicity of that zero. For the y-intercept, we just find out what it is, right? Then we had vertical asymptotes, and we need to determine, okay, does it look like this, or does it look like, are they going both in the same direction? Are they going both in the same direction but down? And so on and so forth, right? And that was determined by, basically, we look at the relevant vertical asymptote, okay, and we check what is its multiplicity. And then the other thing that we check is what did we get when we plug in -2 into the rest of the rational function, right? And if that was negative or positive, that had an effect on what kind of behavior we saw near that vertical asymptote. Then we had to find the horizontal asymptotes and determine whether we approach them from below or from above on either side, from above or from below, okay? So that was another thing we had to check. And then we could also test for symmetry. I guess 4 is kind of optional, but it will help you get a better picture if you check it. And then 5, okay, if we have a horizontal asymptote, oh, I already said that. Okay, and then basically, once we have all the features of our graph, we just fill in the blanks with a smooth, continuous graph. So we did this one, and the interesting thing about this one is it didn't touch the x-axis ever, because the numerator cannot be 0. Okay, there's no way to square a number, add 2, and get 0, unless you count complex numbers, which we don't in this class. And then we had a vertical asymptote at -2 and at +1. Okay, so we ended up graphing this using our group work, and we ended up with a picture which looked somewhat like this. Okay, we had a horizontal asymptote at y = 1. We had a vertical asymptote at -2 and at +1. The behavior near these asymptotes was up and then down on this one, and then on the other one it was down and then up, okay? So once we had like this piece and this piece and this piece and this piece, all that was left to do was to fill in this little gap right here, okay? And since I know it can't touch the x-axis, because the numerator is never 0, so I know that the whole thing should stay beneath the x-axis. The only way for that to happen is for it to turn around. So that's how I filled in the gap. Okay, if you want to see this example in more detail, you need to come to office hours or send me an email. Any questions on graphing rational functions? Okay, then if not, we're going to move on to section 2.5. And what I'm going to do is motor mouth for like 5 minutes and then set you free on some problems. And I'll be walking around, and we'll try to get to most groups. I know there were some groups I missed last time, so if I missed you last time and you want some attention today, just raise your hand and I'll come and see your group. So what is 2.5 about? Well, we've talked about polynomial functions, and we've talked about rational functions, and now we're going to talk about polynomial and rational inequalities. We already kind of talked about these, so it's a little bit weird, but we're going to do it. So P of x, okay, is a polynomial. So let's talk first about polynomial. Let's talk about polynomials first. Okay, so if P of x, P stands for polynomial, okay, has a uniform sign. P of x has a uniform sign on each subinterval of the domain that is subdivided by the zeros. Okay, what do I mean by that? What I mean is that if the function is currently positive, and we're dealing with a polynomial, okay, and sometime later the function was negative, then we know by the intermediate value theorem that we must have at some point crossed the x-axis, right? We have to cross the x-axis. So there's no way for the function to go from being positive to being negative, or to go from being negative to being positive without crossing the x-axis. So what that tells me is that if I map all of the zeros on the x-axis, I know that the sign of the polynomial will go something like negative, positive, negative, or it'll go something like positive, negative, positive, right? It cannot change its sign except for at these zeros of the polynomial. So let's take a look at this polynomial here. What kind of polynomial is it? Well, it's a degree what? What's the degree? What do we call degree 2 polynomials? We call them quadratics. And what does the graph of a quadratic look like? It looks like a parabola, right? Okay, and we can determine whether the parabola opens down or up based on what? the positive or negative value of the leading coefficient. Okay, so it's not clear to me immediately when I look at this, what is the leading coefficient, okay? But if I were to FOIL it out, what would I get? I would get 3x plus 3, and then minus x squared, and then I need one more for, what, minus x, right? Okay, so if we put it all together, we get negative x squared plus 3x, no, plus 2x, right? Plus 2x, and then plus 3, yeah? So what I mean by the leading term is I refer to this as A, and this as B, and this as C, right? And I need to check, is A positive or is A negative? Okay, in this case, we can tell that A is negative, because A in this case is what number? Negative 1. So I know that this parabola opens down. Right? Okay, so it opens down and it passes through the x-axis at these 2 points, which means it looks like this, yeah? Not worrying too much about the details. What I want to show you here is that, look, it's negative until it hits a 0, and then it becomes positive, right? And then it becomes negative again, right? So, in between the zeros, okay, on each subdivided interval, okay, so here's interval 1, here's interval 2, and here is interval 3, right? On each subinterval, the sign, i.e. whether the function is positive or negative, cannot change, okay? Don't forget, by the way, it's possible, it's not necessarily true that if we have a 0, then the sign changes, right? Because what if that 0 is a double root? If that 0 is a double root, then what would we do? We would bounce off, and then it would look like this, right? So it's not necessarily true that a 0 will have us change the sign of the function, but it is true that the sign cannot change anywhere else except for at a 0. Okay, so it's an if, but not an if and only if. Okay, is that clear? Are there questions on this? Okay, so if you want to check the sign for a given subinterval, you just need to pick any old test point. Okay, so I could pick one here, x0, I could pick one here, x1, and pick one here, x2, right? If I pick these 3 test points, and I plug them into the function, and I check whether it is positive or whether it is negative, that will tell me what is the sign of the polynomial on that entire subinterval. Okay? All right. So this is how we tell whether the polynomial is positive or negative. So why is this relevant when we're talking about polynomial and rational inequalities? Because when we have a polynomial inequality, we're going to get everything onto one side, and we're going to get another polynomial, right? And then we're going to check, where is it positive and where is it negative? Well, where is it positive and where is it negative is very much helped out by this notion that I only need to check like a handful of spots to see where is the function positive or negative on the entire real line. Okay, so that's where we're going with this. Okay, so now let's talk about the difference between polynomial inequalities and rational inequalities. The only big difference, okay, is that, okay, a polynomial might change sign at a 0. For a rational function, there are a couple other places where it also might change sign, and I will list those now. The places where a rational function could change sign would be either at a 0 or at a vertical asymptote, okay? So what do I mean by that? Let's take a look at like a rational function that looks something like this. Let's say I have a vertical asymptote here, okay, and my function looks like this, maybe. Okay, let's have another asymptote here. And then on the other side, we'll have it look like this. Okay, so you can imagine a rational function that would look something like this. So where are the places where the function can change sign? It can change sign if it goes straight through the x-axis, just like a polynomial. But there are other places where it might change sign, and those are the vertical asymptotes, okay? And you can imagine why this might happen, because let's go back to our previous lecture and look at this. Let's take a look at this function here. If x goes from being like 1.99, negative 1.99, to being, or why don't I say go from left to right? We'll go from negative 2.01 to negative 1.99. Then what is going to happen to the sign of this factor? It's going to change, right? So there's going to be a momentary moment where the x value is not in the domain, and therefore we don't graph a point, and then suddenly the denominator went from being positive to being negative, which means that the sign of the entire fraction has changed from being, well, whatever it was before to whatever it is now, right? Is that clear? So that's why the sign can also change at a vertical asymptote. But again, it's not necessarily true that if we have a vertical asymptote, the sign must change, because we can have a vertical asymptote which looks like this, okay? We didn't have a sign change. So again, what are we going to do? We are going to subdivide the domain, okay? So we are going to subdivide domain using not just the zeros of the numerator, which of course are the zeros of the function, and using all vertical asymptotes. Then we're going to subdivide the domain into pieces like shown. The first subdivision will be everything to the left of this vertical asymptote. The second subdivision will be everything between that vertical asymptote and the zero. The third subdivision will be everything from that zero to the second vertical asymptote. And the last subdivision will be everything to the right of that vertical asymptote. Is that clear? So we need to have additional subdivisions for each vertical asymptote in addition to the zeros of the rational function. Okay, so these are the places where the function may change sign. So my goal eventually is to solve something like r of x is greater than or equal to 0. So what am I going to do? I'm going to take each subdivision of the domain. I'm going to pick a test point, and I will check by plugging it into the function. Is it positive or is it negative? In this case, I would get a positive number, right? And so I would know that everywhere in this subinterval, the function is positive. Okay? Then I check the next subinterval. I pick a test point somewhere in here, and I plug it in. And if I do, I would get a negative number for this graph. And so I would know that the graph is always negative when the x value lies in this yellow subdivision. And again, I take another test point in the next region, and I plug it in, and this time I would get something positive, and therefore I know that the function is always positive when the x value is in the pink region. And then I would say, okay, pick a test point somewhere in here, plug it in. If I get a positive number, then I know that the function is always positive for all of the x values, all the way up to infinity in this case. Okay? So this is how we're going to solve polynomial and rational inequalities. It comes down to subdividing the domain in the right kind of a way, and then picking test points, right? And then you can imagine if we want to solve something like r of x is larger than or equal to 0, for this one, what are we going to do? We're going to express our answer in terms of interval notation. So if this is like x equals negative 1, this is x equals 1, and then this is like x equals 5, okay? Then what would we say? We would say that r of x is bigger than or equal to 0 when x is from negative infinity up to, we go all the way up to x equals negative 1. Should I include negative 1? No, why not? Because it's an asymptote, it's not even in the domain of the function. How are you going to say that if I plug in this number, it's bigger than or equal to 0? You don't even get a number, much less one that can be compared with 0. Okay, so then I would say, what would the next interval be? It would be from positive 1 up to 5. Should I include positive 1? Yes, because it is a 0. If I plug in 1 to the function, I get 0. So is 0 greater than or equal to 0? Yes, it is. I include it. And then for x equals 5, again, I exclude it because it's not even in the domain. So how are you going to say that it solves it, right? And then finally, we're again positive on the right side of 5. So we should also say 5 comma infinity with parentheses again. And I need big union signs here, right? Union and union. So this is how I would solve something like this. Okay, are there any questions on the theory before we start in on the class activity? So theory for solving polynomial inequalities or rational inequalities, it all comes back to the test point method. Yes?
So wait, if it has to be greater than or equal to 0, what's with negative infinity to negative 1? What is that?
So we're trying to describe the x values such that if I plug them in here, I get something which is greater than or equal to 0. So all of the x values from here on that way, no matter which one I pick, if I plug it in, I get the height of the function will be positive. Even though the x value is negative, the height of the function will be positive. Does that answer your question? Yeah, good question. Any other questions? Okay, then let's try to form ourselves into groups here. We're going to do a class activity on the following. So we have two different problems here. I'll just explain them really quickly. We want to express the solution set of each inequality, just like how I just did, using interval notation, okay? And I'd also like you to draw a number line and shade, okay? So open dots where open dots are needed, closed dots where closed dots are needed, and then shade the relevant regions, okay? So the first one is a polynomial inequality, okay? And for this one, I give you all a hint. The hint is to get everything on to one side, okay? I'm going to move everything over to one side first. And then I'm going to need to find the zeros of whatever we get on the left-hand side, right? Because the zeros are going to be what subdivides our domain. But I caution you that when you do this, you're going to have to find the zeros of a cubic polynomial, right? The way I find the zeros of the cubic polynomial are by using the rational zeros test, and long division, and then we factor. So this is my hint to you. The second one, I give you a rational inequality, and no hint for that one. But if you have questions, you can raise your hand and I'll come around and help you, okay? So please form into groups. If you're sitting far away from somebody, try to group up with someone else. And if you see somebody sitting far away from you, try to incorporate them into your group, please. And good luck. Taylor, can you come down here and work with mine, please? Thanks. Liam, be our partner. You want to work with Alexandra? Yeah, sure. We've got cubic, right? So we don't know that. So the way that we want to we're going to So what we would then do is we would take our cubic polynomial and divide out x minus a. Right? So we need to find a number such that if I plug it into this function, I get a number, right? That's my goal. Find a function such that, or a number such that if I plug it in, and the way we do that is using what we call the rational zero test, right? Which says that if P over Q is a zero of x,
I don't know if we limited this. I just know it helps with big points.
Because like what she asked me, so first you find the factors,
See, the thing is, I don't know. Oh, I already. So the way.
Okay, I want to remind everyone really quickly about the rational zeros test. So I'm seeing a lot of people, they get everything onto one side, and then we say, okay, now what? How do I factor that cubic? Okay, so let's go back and really quickly review that. That was in chapter 2, right? That was 2.3. Here it is. Okay, so what does it say? It says if we have a function a(n)x to the n plus da 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 plus a0, okay, then the rational zeros of this guy are going to be given by p over q, where p is a factor of a0 and q is a factor of an, okay, which means the ones I need to check are, I need to check what are all of the factors of a0, what are all of the factors of an, and what are all of the numbers that I can get by dividing a factor of a0 by a factor of an. And I can check then each one of those to see whether or not I get a 0. Okay, whether or not I get a 0. Is that clear? Not clear? Let's see the example that we had. So we had one here where we had to factor 3x cubed plus da 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 plus 4. The only thing that matters is the number 3 here and the number 4 here. In order to factor it, what did we have to do? We checked, we wrote out what are all of the possible zeros that we can get. Okay, what are all of the possible zeros that we can get? All right. So, and then we check them one by one to see if they are a 0 by plugging them into the function. Once we find one, then we can use long division. We can use long division to reduce the cubic into a quadratic. Okay? That's what we want to do here. So in our case, let's take a look back at our problem. In our problem, we have what? I think I might have wrote it wrong on your paper, by the way, Kevin. Let me think about that for a second. So on ours here, I'm going to move this down a little bit and this down a little bit. What do? We move everything to one side. So I get x cubed minus 3x squared, and then minus 4x, and then plus 12, right? So A0 is 12, right? So what are the factors of 12? We've got 2, 3, 4, 6, 1, and 12. And what are the factors of AN? Well, AN is 1, so the factors of that are just 1, right? So the possible zeros, what are they going to be? They're going to be whatever we get when we take one of these numbers and divide it by 1. Well, that just means we get one of those numbers, right? So the possible zeros could be 1, 2, 3, 4, 6, 12, and also plus or minus any of those. Okay, so hopefully that helps us get started. We need to check each one and see. We go until we find a 0, then we divide it out using long division. Yeah, so if 3 is a 0, then we do know that x minus 3 is going to be a factor, right?
Yes, and you don't even have to do that. You can just do this.
Minus 27.
Oh, yeah, we're gonna figure it out.
Is this some kind of synthetic division? Yeah, you can do synthetic division if you want. I don't use synthetic division. But yeah, that's totally fine. If it works for you, then go ahead and use it as long as it's right.
Okay, if I use
Oh, okay, yeah. Oh, yeah, that's fine. Yeah, you're big method. Do I have the answers, or do you?
It's fine.
No, but I can check. Let's see. X cubed minus 3x squared. Oh, wait. We want minus 4x. I'm looking for that. Right? Minus 4x. And then plus 12, right? Let's check. Should be getting something. Yeah, I think so. What's up? Did you have a question? Right. So what was confusing about x squared minus 4? So the whole point of the long division is to say that, look, this polynomial here, x cubed minus 3x squared minus 4y plus 12, that is equal to x minus 3, or factor, times what we get from the quotient, x squared minus 4. Yes? So if I want to factor this whole thing, I first use long division to rewrite it as the product of a linear factor and a quadratic factor. And if I want to fully factor this, I still have the left to do. I need to factor the quadratic factor, and then I'll have it all the way factored again.
Is x squared minus 4y?
Yeah. Oh. So how do we factor that? Difference of squares. X minus 2x plus 2. Okay. You're so confused, you need help? Okay, so at the end of the day, we're trying to figure out whether it's positive or negative on each subinterval. So we found these subintervals. I got that. Figure out, well, that subinterval is the polynomial negative or is it positive? So the way we do that is we pick a point and we plug it in. We know that it can only be at 3 points. So it's either something like positive, negative, or something like that, or it could be positive, negative, negative, right? But we know that in each subinterval, I can check what is the sign of this thing by plugging in just one point. So I need to pick a point like 3, 0, and then something between 2 and 3, something bigger than 3.
That's my method is when you choose like a number, you just plug it in, right?
Right, so what I mean by graphing on a number line is eventually you'll get something like, you'll get an answer in integral notation, right? In terms of like, what are the numbers that I could plug in? And when I graph something in integral notation, like for example, negative 2 with a parenthesis like that, what I do, when I use my graph on a number line, a thing here, and then a circle in here, and then a closed dot here. That's what I'm talking about. Yeah, no worries.
Yeah, we're in the long division.
Okay. Have you guys gone through the long division part?
The 3 zeros had to be your long division.
Well, how do you find the 3 zeros without doing long division? Oh, okay, I see, you need to use the rational theory. It turns out that all the zeros are rational. Okay, so here's what I had in mind.
So we are good. This is
Okay,
great.
so you found a zero, right, which is this 0, 3, right? So you determined that x minus 3 should be a factor, right? So from here, what are we gonna do? We're gonna do long division. Okay, just a graph. So how do I start? It's just a graph.
You wanna get rid of this?
You wanna get rid of this x cubed, right? What do I need to multiply x by in order to make it cancel with x cubed? I need to multiply x squared, right? So here comes an x squared. You get 2 because we can't write backwards.
I'll be there.
Okay, perfect, x squared. So, now what do? I put a minus sign here, and I do parentheses, and what do I need to do? I need to multiply x squared with x, multiply x squared with negative 3, and write those here. So we get. Very good. Now, I need to subtract. So what I'm gonna do is I'm gonna subtract underneath this, division sign. So I'm gonna take x cubed minus x cubed, that just goes away, right? And then what do I get when I do negative 3x squared minus negative 3x squared? It also cancels, right? So what am I left with? And I should also have a plus 12 here, I think.
Oh, yeah.
Okay, so now we need to check, now that we got this, we bring this stuff down, yes? So we have that minus 4x and then plus 12. And now I need to check, what do I need to multiply x by in order to cancel out a negative 4x? I need to multiply by negative 4, so we put here a negative 4. And now, we multiply that out. That's where we have to be careful because we are subtracting all of this, right? And then it cancels, right? Okay, so what have we shown? So we do the long division and we say, okay, if I take this cubic polynomial and I divide it by x minus 3, I get a new polynomial. That polynomial is x squared minus 4, which is to say,
You can multiply them and then we get that.
exactly, which is to say that this cubic
Wow.
polynomial is equal to x minus 3 times x squared minus 4, like shown, right? And so if I want to factor this ultimately, what have I done? I take one linear factor out. If I divide a cubic by a linear, I get a quadratic. And now I can factor the quadratic using any method I want. So this method, okay, got a little lucky. We had all rational zeros. So we're able to test them all and find them all, right? But realistically, what we want to do is find one and then use the long division, because it's possible that there are zeros that aren't rational, right? You could have like a square root of 2 as a zero. Does that help? Okay.
Wait, is that the only?
So I found neighbors.
I found that pretty easy. So then, I went and put it into long division.
It looks like you're almost done.
Yeah, but then.
So you want to do
Okay, so you got all the way to the bottom of this. What does this mean? This means if you divide out the x minus 3 factor, the answer is,
Sorry, I didn't see what you were doing.
we have 1 here in the, oh yeah. So wait, let's see. I mean, this is kind of right, but.
well, I mean, you could have done it too, but you Well, if you would have been, because how we got
You should get something like x squared minus L squared here. So this is looking right at 1 and 4. We have 1.
Because when I went like way down and I was multiplied, you just like
Interesting.
yes.
Well, in any case, think about it this way, right? If I want to divide in x minus 3 with x into here, right, what do I need to do? The first thing I need to get rid of is just x cubed. So I multiply x with x squared to get rid of the x cubed. So I subtract x cubed minus 3x squared. So if I subtract those, these ones cancel. And I'm left with what? This rate comes down, and I'm left with 4x, and I should be able to minus 4x. And then that's plus 12. Okay, so now we're here. So now what do I need to do? I need to get rid of the negative 4x. So I need to ask myself, what do I have to multiply x with? To get rid of negative 4x, I need to multiply by negative 4, so that's why I put a negative 4 here. So then I get minus negative 4x minus plus 12. If I subtract negative 4x from negative 4x, it goes away. Subtract 12 from 12, it goes away. So I get 0. Because I knew I was going to get 0 all along because 3 is a factor. Right? Minus 3 is a factor. So this is to say that I can rewrite x cubed minus 3x squared minus 4x plus 12. I can rewrite this as x minus 3 times x squared minus 4. Close. Difference of squares, how do we factor? It should be x minus 2 and then x plus 2, right? Okay, so at the end of the day, we can rewrite this like you said, right? X minus 3 and then x plus 2 and then x minus 2. Yeah? So what do? The whole point of long division was to say, well, I take a cubic polynomial. If I can divide a cubic polynomial by a linear polynomial and get a quadratic, then I can rewrite the polynomial, which is originally cubic, as the product of the linear factor and the quadratic factor. Okay? And this one, I know how to factor. So at the end of the day, I get the complete factorization of this cubic polynomial. Okay, you know where to go from here? Okay, well, it's up on the board. We've got it fully factored. What we have to do next is test point method.
So we're gonna.
Hang on just a second. I gotta go through it first.
Use a little.
All right, what's up? Less than or equal to 0. Right? You want to factor this is a polynomial. You want to check where is it negative. We know that it will be negative on maybe some of these. We know that it can't be negative this point, this point, and this point. So to check
You could use 0. Well, 0's not.
this makes it check whether it's positive or negative.
Probably should have written
Like take a test point, say, right or not.
Yeah, from the different sections of
After I
Alright, what's up?
Yeah, you put the zeros on the number line, well, the 2, -2, and +3, and then you pick, you like,
Okay.
separate it into sections,
I can find that.
and then you, between each other, and then you
I mean,
pick
Oh,
out,
I got it.
and then you find, and you see if it's
So,
right.
if you wanna write it that way, that's totally fine.
I don't know, we're not, yes.
Here, maybe I can, here, so I can write, I'm gonna go right in the middle here, I have two papers. I'll write it right here. So what do? We take our function x cubed, minus 3x squared minus 4x plus 12, right? We long division by x minus 0, something like that. So you find one of the zeros, and now we're going to divide it out with the hopes of creating a quadratic expression.
That symbol is just whatever x can't be on the.
No, I
We found the intervals on which is true, right?
But I want the beginning.
Like, oh, wait, that's easier.
It's just a
Okay,
lot.
so
We can set point and then we plug it into the graph.
That would be like, whatever you call it.
Something positive versus something positive, that means it's something negative. So it's negative in this region. Well,
This one is.
so you want to check where it's negative, so
I put it all down below.
and then once you just express our answer.
Yeah.
But this is our, doesn't want to be anything, so that's what we're
As far as I've gotten.
So like, the way, this is how we use it. This is.
Really?
It is a basic question. It could be.
The only thing I said was shade on this one, which means I want to see you do like, you know, like a shade where it's close up here, it's true, it's close up, don't shade here.
I'll see when I go to the store. Probably because we don't have a kitchen. Look at
If we're checking.
Plug in 1, 2, 3 right now. Thank you, actually.
Okay, yeah. Yeah, okay.
Where is this, which is this? Where is this? Negative.
There's a game
right?
like
So we do like
Halloween.
we
Yeah.
have numbers which make it
Yeah. It's
negative
just
2,
like
2,
extra night.
and 3. So negative 2. So, we want to check where
No.
negative. We know that it's
No. Because
No.
the way it goes.
No, you can't. Like what I mean,
And if it's true, then we'll shade that region. If it's false, then we won't shade that region. And then we'll transform that into shading. Does that give you something to go with?
I still want to wait.
Anyone else have more questions? Okay, question?
All right, we're doing it. Wait, hold on, let me actually take that.
Okay, so once we've gotten to here, right, what do we have? We have the rational expression, correctly find the common denominator.
What says no?
We still have larger than or equal to 0. We know that a rational function can only possibly change sign at a 0 to the greater or at a vertical asymptote, which we can see exactly where those three things are going to be. So just like with the polynomial, we're going to do a number line.
Well,
And the number line, we're going to put
listen.
on 1, 2, and 3.
No, they're red and it's coming out in the, we've already.
2, and 3. So, since the polynomial can only change sign at these three number positions, if I check a number to the left and in the middle and in the middle and to the right, test points. If I determine that the rational expression is positive with any number which is smaller than 1, then I determine that it is positive or negative for every number which is smaller than 1. And then same thing for between 1 and 2, same thing for between 2 and 3, same thing for big 1. This, yeah, exactly. So if I plug in, let's try it, okay, let's take a test point like 0. What do I want to check? I want to check when I plug in number less than 1, is the rational function going to be positive or negative? So let's try 0. If I plug in 0, I get negative 3 on top, negative 1 and negative 2 on bottom. So I have a positive on the bottom and a negative on the top. Is it negative or positive? It should be negative, right? So I should assign negative here. So, do we think it's true or false? I think it's false for this region, so I'm not going to. Now let's try 1.5. If I do 1.5, I get 1.5 on the top, or negative 1.5 on top, I get half, and then negative half on the bottom. So negative on the top, negative on the top, positive number overall.
You're like in the middle.
So between 1 and 2, the rational function is positive. I am going to shade here. And then, what should I put at 1? 1 is a vertical asymptote, so it's not even in the domain. So I'm going to put an open dot here. Right? How about at 2? Again, not even in the domain. So I'm definitely not going to put a closed dot at 2 because it's not in the domain. Right? Now I need to check between 2 and 3. What do? I take 2.5, put it in here, here. Check if it's positive or negative, and so on. Did you get that as well, Griffin?
I mean, I had the answer, but then I had to question myself.
Okay.
Like, I have the correct answer.
Alright.
But why is it so weird?
What the heck?
Are we doing over here? Struggling?
Yes.
Which one are we on?
The second one.
Okay. Okay, so for the
Wait,
second
you
one.
need to like go back to the other one. Did you finish the first problem?
No, I got to like where yeah.
I think I did this for
Not the coordinate plane, you just have to open the number line. Last. You know what?
So we factored this guy, right? We factored this guy and we get the resulting x minus 3 times x plus 2 times x minus 2. And it should be less than or equal to 2, right? This is what we want to check. So we do a number line, we put on negative 2, and then 2, and then 3. And I need to check a number to the left of negative 2, between negative 2 and 2, between 2 and 3, and bigger than 3. And what do I do with those test points? I plug them in here, and here, and here, and I check whether it's true. Then what do you express the interval where it's true or not?
That was just me trying to make some class.
You can ask Laura, bro.
Don't ask me, I'm barely making it by.
Each interval.
Everything's going pretty bad.
No one said that, I just said no. You guys are really
Okay, so
Then wash them yourself. That's the issue.
Always salt.
Do you know the partial? She's one.
I think it looks like that.
Oh wait,
Listen, I need to just like put it in my door, like I'm here, I was walking there, like, yeah,
I get 0 options.
I don't know how to find it.
Now, if this was.
And one, so both of these.
That's
are
really
plus
so
is
okay, on your search.
positive opposite.
Okay, I'm not really so tired, so tired that I come out like me.
I mean, I
These three things all use the same thing. Okay, so this has values of x, which makes those values of x can be expressed using these are those x that will make the inequality.
So you're not like real quick.
You graph of those numbers. I think for that number.
Oh my God.
His refer to their as minus cos
stay all the way up top.
Honestly,
It's just another representation.
I'm getting too fast. Oh my god. Dude, I want to flap more.
It is.
I'm ready to go.
Yes.
Okay, how are we doing?
Fantastic.
We got a few minutes left of class, so maybe what we'll do is we'll take a look at some of the key features. We'll take a look at some of the key features of these ones. So let's start with the first one. The first one said we want to check where is this, what, less than or equal to 0? Yeah, less than or equal to 0. Okay, so we guess a 0. Okay, whichever one you guess might be different, but if I guess the one x equals 3, then I know that I can do long division. Plus 12, and I divide out x minus 3. The goal of the long division is to rewrite this function. If I divide that function by a polynomial and get another polynomial, then I know that this polynomial is equal to the product of those two. Like so. Which is also equal to x minus 3. Now I can factor this one because it's quadratic, right? Times x minus 2 times x plus 2, yes? And I'm supposed to check where is this number less than or equal to 0. Okay? I'm supposed to check where is it less than or equal to 0. So now what do? I make a number line. And I put on the number line, I put -2 and then 2 and then 3. So from each subinterval, I'm going to pick a test point like -3 or 0 or 2.5 or 4. And I'm going to plug them in. Where am I going to plug these numbers in? I'm going to plug them into the function. Here, here, and here. If I plug in -3, then this will be -6 times -5 times -1. So, is it a positive number or a negative number? It's a negative number. So is it true or false?
True.
It's true because a negative number is less than or equal to 0. Therefore, I am going to shade this region. Am I going to shade at -2? Yes, I am. I am going to put a closed dot here because if I plug in -2, what do I get? When I plug it in here, I get 0. And so therefore, the entire left side will be 0. And 0 is in fact less than or equal to 0. Okay? All right, next up, I plug in 0. What do I get? -3 times -2 times +2. That's a positive number. So it's false in this region. Then, the next region, I plug in 2.5. What do I get? This would be a negative number times a positive number times a positive number. So it's true. And again, I put closed dots here and closed dot here. And then if I plug in 4, what do I get? Positive, positive, positive. Definitely not going to be a negative number. So it's false in this region. So my answer would be the intervals -infinity up to 2, union 2, 3. Any questions on that one? Okay, I'm low on time, so if you have questions, please email them to me or come to office hours. I want to show the other one too. So for the other one, what do? For the other one, we need to get everything onto one side again. So I rewrite this as what? I move this like so. I put this guy to the other side, and I'm subtracting those two, and I get 0. So what I'm supposed to do is then combine these guys. Combine them using a common denominator. So I get 2 times x minus 2 all over x minus 1 times x minus 2 minus 1 times x minus 1. all over x minus 2 times x minus 1 is larger than or equal to 0. If I combine these, 2x minus x, I get x, and then negative 4 plus 1, I get x minus 3 over x minus 1 times x minus 2 is larger than or equal to 0. Again, I make a number line. And what needs to go on the number line is anything that makes the numerator 0, that would be a 0 of the function, and anything that makes the denominator 0, that's where I have vertical asymptotes. So I put on the number line the numbers 1 and 2 and 3, and I pick test points from each subregion like 0, 1.5, 2.5, and 4, and I plug them in. Where? Into the function. If I plug 0, I get negative 3 over negative 1 times negative 2. What kind of number is that? Negative, right? Should be negative because the bottom will be positive, the top will be negative. So this is a negative number. So is it true or false at 0? It's false because we get a negative number which is not positive. So it's false here. Then we plug 1.5, and so on and so forth. Do I have enough? Yeah, I got 2 minutes. I can finish this. We plug 1.5. What do we get on top? We get negative 1.5. On the bottom, we get negative 0.5 times 0.5. Well, the other way around, sorry. Right? So the bottom is going to be negative, and the top is going to be negative. So the whole thing is going to be positive. So it's true in this region, right? Okay, so I'm going to shade here. Now let me ask, am I going to put an open dot or a closed dot at 1 or 2? I say, let's do a closed dot because we always have closed dots when it's a larger than or equal to, right? Wrong. Why? Why wrong? Because the bottom would be 0. Okay, so it can't solve the inequality because it can't even be plugged into the inequality. So I'm going to put open dots at 1 and 2. Then 2.5, on the top I'd get a negative, on the bottom I believe I would get a positive, so it's going to be a negative number, so it's again going to be false here. How about from 4? Well, at 4, the top is positive, and then positive and positive on the bottom, it's definitely going to be true. So at 4, we're going to shade. And what kind of thing am I going to put at 3? Another open dot? Why closed dot? Because it's fine. You can plug in 0 to the top. There's no problem with that. And I would get 0, which is larger than or equal to 0. So I put a closed dot here. At the end of the day, my interval goes from 1 to 2, and I union with 3 to infinity. Okay, so that's it for today. Thanks for your attention. See you next week. Have a good weekend.